ଗଲେ ତେଲ ଗ୍ୟାସ୍ ଦ୍ୱାରା ଛାଡିଗଲା ଆଉ ଏରା ନଖରେ ଛଡେଇଲେ ଫୁଲିଯିବ। ଯଦି ତମେ ଯୋଉ ନଖ ମାରୁଛ ମୁଁ ନଖ ମାରେନି ମୁଁ ରେନ୍ଥି ଦିଏ। ହଁ ହଁ ହଁ।
Am I audible? Good morning.
Good morning, sir. Yes, you are audible, sir.
Yeah, can you please confirm I'm audible or not?
Sir, you are audible. Hello,
Okay.
sir. You are audible, sir.
Okay, thank you. So let
Can
me
you
just
hear me, sir?
Yes.
The program will start soon. It will start around 11 a.m. Please wait.
Okay.
2 minutes.
So let me project my presentation. So can I share my screen right now? Just for checking.
Yes, yes, yes. So you can share.
But it is disabled. It's saying that host disabled
Okay.
attend.
1
Oh,
minute. sir.
disable attendee screen. Hello. Okay.
Hello, sir. Now you can try.
Okay. So are you able to see the screen?
Yes, sir.
Okay. So I'm going to stop sharing. So after introduction, I'm going to share it again.
Okay, sir. Okay. Now, good morning, everybody. Welcome today for the session of Dr. Parameshwar Das. We'll start around 11:05. Just a few more minutes. 5 minutes.
സൗണ്ട് കേൾക്കുന്നുണ്ട്. Poranshu Das.
Hello, Sandeep sir.
Okay, sir.
Please start the session.
Okay. Good morning, everybody. Am I audible to everyone?
Yes, sir.
Okay.
Yeah.
Today, on the last day of our FDB, like next generation technologies in electronics and computer science trends and approaches. The FDP of 5-day FDP is organized by Greater Kolkata College of Engineering and Management. Today, Professor Parameshwar Das, Professor of GNIT, is going to present his topic. A brief intro of Professor Das. He's a master of statistics from ISI Kolkata and a BSc honors in statistics from Ramakrishna Mission Residential College, Narendra. under University of Calcutta. His profile is glorious. He has almost 35 years of work experience in software system architecture and design development, re-engineering, product development, and digital transformation. He has worked on various technologies, object-oriented programming, web applications, e-commerce applications, service-oriented architecture, enterprise data and application integration, cloud computing, data warehouse, data mining, data visualization, big data, data analytics, data science, AI, ML, generative AI. He has worked for TCS for around 33 years and 2 years for Tata Motors, or which is also known as Telco Limited. Also, he was a visiting lecturer on statistics at undergraduate level for 1 year at Brahmananda Keshavchandra College, Kolkata. He has played key roles and responsibilities such as software engineer, technology center of excellence at Oracle Middleware Regional Director, Data Architect, Data Scientist, Enterprise Architect, Chief Architect, and Technology Mentor across the globe. His business domain experience includes telecommunications, finance, insurance, logistics, oil and gas, metal and mining, utility, media and publishing, transportation, and retail. His passion is problem solving with applied mathematics, statistics, and modern computing. Now, Professor Das, the platform is yours. You can start this session.
Thank you, sir.
Okay.
Thank you.
Welcome. Sir.
So let me share the screen. So is the screen visible?
Yes, sir. The screen is
Okay. Good morning, all of you. I'm privileged to be a speaker for such a prestigious uh, faculty development program. So, as I've been introduced, I have very recently joined academics, less than 2 months ago, and my entire career on industry. So today I would like to talk on like what is the latest and greatest computing, and how the computing can be, computing environment, computing platform can be leveraged for building the today's
हा.
application.
त्याच्या पुढे तुम्ही जर अजून याच्या पुढे केलं ऑन
Yeah, mute please. So my topics is the cloud native computing for building modern applications. So probably the cloud computing. So I'll talk on basically what are the basic, cloud computing building blocks, and then I'll switch to what is the demand for the modern computing or modern applications. The topics that would be focused today is the cloud computing engine, the basic computing engine, and what are the different drivers like modern applications. What does it mean? What is the modern applications definition, requirements, and necessity, and how the cloud native computing is going to help to implement the modern applications. And there are various components. One of the component, the most important component, the cloud containerization, then the serverless computing, and certain tools and technologies and on use case. So time, I think this is 2 hours time, and this will be a very enriched session. So what do we need for modern software applications? So as you know that to build and run software applications, we need the data centers where there'll be a set of machines, different range of machines, small, medium, large, different kinds of servers, different kinds of softwares, different kinds of network. So the modern computing demands a data center must be having the optimized cost, because cost is the main driver everywhere. Okay, we cannot avoid the finance. So how we can think about the data center, okay, with set of machines, set of softwares, technologies, which will run on very much optimized cost. In other words, so probably the shared service or the paper use, so those are required. The flexibility of technology, programming language, and database. So today there are lots of technologies are there. Infinite number of technologies, the programming language, the database, okay, the middleware, API. There are variety of technologies, variety of product vendors, okay, and we can think about a platform where there will be flexibility of technology, like like 20 years back, like 30 years back, or 25 years back. So we didn't have that kind of luxury. So either you will implement the application using C++, okay, the whole application running on maybe Unix or Linux, or you can think about one application based on, okay, Java or say .NET. So one massive applications, okay, software applications which you run on typically a monolithic one programming language, one particular database. But today there is a luxury that I can pick and choose the technology. Even for the same software that you are going to build, like you are building on, say, think about building a software for a logistics supply chain management, or think about a software for a manufacturing industry, think about software for building a oil and gas industry. So it will be massive in large, because there are variety of uh, business functions, nature of business functions, and variety of technology. So there should be some flexibility where I can pick and choose. Okay, if there are, say, for example, like a team of 20 members, a team of 30 members. So some people might be conversant with, say, programming language like, say, Java technology, which is very one of the popular. Some set of people, they might be interested to work on, say, traditional C++. Some set of people, they are very much conversant with the very latest technology like React, JavaScript, Node.js. Some set of people, they may be interested for Python. So can we think about one software application development platform where this variety of technology can be plugged in as you like? So the flexible technology, because this 10 lines are extremely important, like to understand what is the necessity of the modern software applications.
Excuse me, sir.
Yes.
Excuse me. Sir, is the slide is changing? Actually, we are seeing the front slide, the number 1 slide. Is the slide is changing? Are you changing the slides?
No, see, the slide is the like what we need for modern software application.
Okay, thank you, sir. Sorry for the interruption. Yes.
Thank you. Okay, I'm taking a little time because these are the drivers for for the session, like for subsequent discussions will be based on these parameters. A little more time for this to explain, like what is the demand now. So data center flexibility of technology, faster deployment, because your depth and breadth of the business functionality is growing rapidly. So you need more infrastructure, more machines, and then fast deployment across the physical data centers or virtual data center. So you have to deploy quickly. When you say deploy, it's very fundamental, like, for, you install the software. Say you should have a machine with, say, operating system. Then you need to install maybe certain, compiler like, say, Java, Python, C++. You need to install database. Okay. And then you build your applications using the programming language and, deploy on that. So the faster deployment across, if you have, say, 10 machines, and if you need to install, if you need to install, so traditionally it had taken a lot of time, because you need to set up the machine individually. You go to machine number 1, you install, and ensure that operating system is there. You install the database, install the, say, maybe Java compiler, or say Python, or say Node.js. Okay. Then now you create your application binary and go and deploy that, and change the, environment variables, and then you can deploy. So deployment on individual machines for the same software, it takes a lot of time. But today, demand is that agility. So a software application that has taken 1 year time, in my career, I've seen, like, like 30 years back, 20 years back, 15 years back, like, the project, was spanning, the time was, 1 year, 2 year, 3 year. And today it is 3 months, 6 months. You have to complete the same thing within the smaller amount of time. So very faster deployment across the data centers, across your machines is necessary. Application scalability. So for, you understand, for any application, software applications, who are the, stakeholders, the users. It's like, say, e-commerce applications. Okay, like, say, any Blinkit, very small applications. So we citizens, we are the user. Any e-commerce application like Amazon, Flipkart, who are the stakeholders? We citizens of country. So every day, like, number of users is increasing. So it's an infinite scalability is demanded for the software. So this means, if today, if there are 1 million users, and if tomorrow there is suddenly 1.25 million, so my software should not crash. So can we have certain platform that will be supported for this? So infinite scalability in terms of number of users, in terms of functionality. So day by day, new functionalities are getting added. New functionality on the same domain. So you have to think about one application architecture, think about the platform architecture where this will be supported, okay, with the minimal cost. We should not forget that. So because of this scalability requirement, so the obviously automatic auto scaling infrastructure, auto scaling is also required. This means your compute, your storage, your network, your application, okay, should be automatically scalable. So this means, if my number of users for the application is growing from, say, 1,000 to 2,000, 2,000 to 3,000, so your platform should be scalable automatically, because because it's a agile world, so nobody's going to wait. Okay, so therefore, like, the auto scalability of the infrastructure is also one of the key requirement for building the modern software applications. Low latency, high throughput. This is a very fundamental requirement. So latency should be minimal. If you are going to make a query, going to place an order in e-commerce, so your time should not taken, okay, more than 10 seconds or 15 seconds. So it has to be low latency and high throughput. So lot of orders can be placed, lot of processing can be done, lot of payment can be done, lot of messages can pass from from the pipeline over the internet. It can be infinite. Fault tolerance, high availability. So your software, it should not, like, minimum 99%. There should be 99% uptime and very minimal downtime. So this means your applications, your infrastructure should be available, okay, almost like 24 hours, almost 24 hours a day. So who will be able to provide that? Is it possible, like, if I create a data center like that you have did in last 10 years, 15 years, like we will buy the machines, buy the softwares. We are continuously upgrading the operating system, continuously upgrading the softwares, like
Sir, slide is not changing. Sir,
yeah, I know that. I know.
not
Still, I'm there on the first slide. I'm still there on the first slide. What we need for modern software applications.
Okay, sir.
Okay. So fault tolerance, high availability is requirement. Major natural disaster. So suppose there is a earthquake, there is a flood, or a particular region where your physical data center is located. What will happen? Like if there is a massive level earthquake, massive level flood, or any natural disaster. So what will happen to you? Because your software is today's software is being used by people across the globe. So just because of disaster in one particular place, your software should not be down. So therefore, I need a platform where my software should be available to the users. Doesn't matter whether there is a disaster in a particular place. So we need this answer. Who is going to give that? Data residency. So there are a lot of requirement today that data. Now all the countries, so they are talking about like their data should be residing in their data center in their within country only. Like India government, the METI complaint. So they are demanding that your data should be in India. European people, they are saying the GDPR. So their data will be within Europe. Okay, you may process it anywhere, but the data has to reside over there. Multi-location workload for multinational, all the big multinational corporates. So they're having business across the countries. So they want their workload, their data center should be distributed across the globe. They don't want the data center like say Apple. They don't want that their data center only will be in North America. They don't want, because they are having business across the globe. So they want the distributed data center. So all these things are required. Okay, by when I say the modern applications. And also, what is this modern computing pattern? Like the first, are you able to see this diagram like in modern computing pattern? So
No.
yeah, so here, like that for any software, like I'm giving the example again, e-commerce. So so there are certain applications which will the computing pattern is on and off. So there are some process will run, okay, maybe at like in the typically banking process. So some process will run maybe at end of the quarter only, like for example, like interest calculation, okay, for say account interest for the fixed deposit accounts. So that happens, that compute that calculation, that process runs only once, maybe end of the quarter. So this means there are certain applications which are running on and off. Okay, so you need the computing accordingly. So if there is no need of the computing environment, so why should I consume the resources? If I know that my interest calculation for bank, that process will run only like end of quarter, so this means 4 times in a year, why should I procure my why should I procure my license? Why should I procure my machines? Why should I procure my operating system, platform software, like 365 days? So we should have, as I said, that like the cost optimization is one key parameter. So if there is a pattern like on and off, so probably your hardware, software, network, everything should be kind of on and off mode. So whenever, maybe at end of the quarter for that banking purpose, okay, when the interest calculation will happen, so probably I need the resources only that time. Remaining time I should not spend any money. Is it possible in traditional computing? No, it's not possible, because we buy the hardware permanently, we buy the licenses for software and we install. We don't use it. We use only at end of the quarter. So this is a classic example, like this modern computing pattern should be supported certain platform, which is nothing but the cloud computing. Growing fast for majority of these applications. Okay, so obviously business is growing. So this means more users are joining, more functionalities are there, and more computing resources are required. So there is a growing fast, so there is a pattern. So as and when it is growing, I would be able to consume my resources accordingly. It's not that I will buy the resources which will be required after 5 years. No, I don't want. I want to spend money. I want to set up my environment. Okay, I'll set up my compute, network, storage, application, database, everything like based on today's need only. So tomorrow there is another requirement. So I want that flexibility that it will automatically scale up. Okay, so in traditional computing, within your data center, that is not possible. Unpredictable bursting. So in spite of this, you even if you plan for next 5 years, 10 years, but still there will be spike. There will be certain, maybe during festival time, okay, in the e-commerce, retail orders, that that platform, number of users, suddenly grows very, very extremely high. Okay, so sometimes there is an unpredictable bursting. So therefore, my application should not run, my compute should not fail. So I want, so this demands a software platform, this demands a hardware platform, it demands a network platform which will support this. Okay, there is a predictable bursting that where there is a there is a pattern like sinograph. So there will be at certain time points in a year, throughout the year, maybe 4 times, 5 times. Okay, there will be a spike for the application resources. Okay, computing resources. So there will be an up and down. So all these things, okay, I should have some flexibility. In majority of the cases, either you oversize or you undersize, and that oversize will be there throughout the year. So which is not good, because I'm not utilizing it. I'm consuming money. So I'm unnecessary. We are consuming the resources, or you are going to undersize it. So this means whenever there is a spike, so it is going to fail. So I want an answer, fit for the purpose, and only cloud computing can do this. So what is the cloud computing, basic cloud computing architecture? So this is very much like, a massively scalable, like, lots of machines are there. Okay, machines, storage, okay, they are into some places, in some global place, okay, that we do not know. Okay, and we get based on my need, based on the need for a particular organizations. Okay, like say State Bank of India, for example, for their banking need, they need to have the computing engines. So they need the compute, storage, networking, security, all these things they need. So what we'll do? So they have to provision it at least. So based on my need, there is an infinite number of servers are lying somewhere. We do not know actually. Okay, and based on my need, I'm going to consume that. I need 5 machines, 10 machines, 2 machines. I need in the machines, maybe some machines with Windows software, some machines with Linux, some machines with Red Hat Linux. Okay. So, and I need for certain machines, I need database, for certain machines, I need Java, for certain machines, I need Python, Node.js. So I want, I don't have time. So I just, going to log in into the certain cloud vendor, okay, with the cloud vendor's website. So I will say that, I want to provision for, say, 10 machines. So, and I will say that, and the 10 machines will be within one particular network. So within 10-15 minutes, you will create a data center. Is that possible in physical data center? No. You spend like 6 months time. You take a quotation from different hardware vendors, different software vendors. Okay, and you buy it. Somebody want to ship it in a machine, have a air condition. Okay, AC, fan. So it takes 1 year time to data center. If it is cloud, within 1 day you can create a data centers of 10 machines, 15 machines, 20 machines, 100 machines. Okay, so that is the cloud computing. So whatever driver side, whatever need I have mentioned, okay, all these things will be answered throughout my session. So using cloud computing, I can create a data center with n number of machines, okay, with various operating systems, various database, various programming language, okay, various machine learning, IoT, blockchain, whatever you like, anything and everything, you will get very, very easily. So I don't want to spend time. So I'm quickly, going to, so this slide is the cloud global infrastructure. So all these things will be answered, as you mentioned, that will be by the cloud infrastructure. So how I'll spend, few minutes time. So how, these global infrastructures are, created by, by cloud vendors. I'm in Kolkata, okay, someone in Mumbai, someone in Delhi, someone in Singapore, someone in Australia. So they have created a global regions. This is more or less true for all, the cloud vendors like Amazon, Azure, Microsoft, or say, Google, Oracle, IBM. So there is a region concept. Okay. So I'm in Kolkata, say I would prefer to procure a machine probably which is residing within Kolkata or maybe nearby. Someone who is there in, say, New York, say he would like to have a machine, okay, probably the machine should be residing in, close to New York City. So cloud has given me a set of regions across the globe, okay, and within region there are n number of physical locations, okay, where your data center will be there. So they have the set of machines, and from there only I'm going to procure a, one or two machines or 10 machines from them. So like, for example, like in Mumbai, so Mumbai is for India, Mumbai is one of the, key region for all the clouds. Okay. So within Mumbai, so there are set of physical zones which are called availability zones, like North Mumbai, South Mumbai, for example. Okay. So there may be Pune, another zone. So this means they are keeping their hardwares, their servers, machines, everything within that, regions, and a set of, like, one region will consist of a set of zones. See, one zone, as I said, if I say that Kolkata is one zone, unfortunately there is no zone in Kolkata. So if I say that North Mumbai is one zone, so within North Mumbai, maybe like, 1,000 machines are there. So from there you can provision. When you are asking cloud, you give me one machine, one laptop, one, I call it virtual machine. So you have to mention from which region you want and from which zone you want. And obviously, like I would look for a machine which will be there in a zone and region which will be proximate, okay, close proximate to my area, so that, there will be a better throughput, okay, the better response time. Okay, so this is the, like, concept, like,
Hello,
region.
sir. Excuse me, sir. Dr. Das. Excuse me.
Yes.
Extremely sorry to interrupt you in the middle of the session. Sir, are you changing the number of slides? Hello.
Yeah.
Sir, actually what is happening, I think your slide is in PPT format, right?
Right.
Sir, the in Zoom meetings actually you are changing, but we cannot see the change of slides. Okay, it's showing the number one slide, slide number one. Okay, everybody is being number one slide. You are supposed you have gone to number 10 or number 15 number
Yeah.
slide.
So right now I'm on the slide heading is cloud global infrastructure.
No. It's not showing, sir. Everybody is actually asking so. Yes, this slide is not showing. Sir, may I
Okay.
suggest something? There is a problem with Zoom. PPT don't show the change of slide. Sir, do you have the PDF version of this slide?
Oh, it doesn't support PPT.
Yes, yesterday also this technical problem occurred with the speaker. PPT, the change of slides is not showing. Sir,
Let me try one second. If not, then I'll create a, I'll quickly create a
okay.
PPT.
Or else, sir, will you kindly please change the extension to PDF, and then it will show the change of slides.
Can you check once again, like,
Okay, sir, please check. Change. I'm visualizing now.
Are you able to
Yes,
see
yes.
this slide?
Yes, yes. Now changing.
So when you select manually, then it's the change of slide can be visualized. Well,
Okay. Actually, I put the presentation in the PPT in the presentation mode. I don't know whether that is the problem or not.
oh,
Yes,
Like,
yes. Presentation mode, the slide changing is not visible here.
Ajay, can you please confirm whether you are able to see the cloud regions and availability zones? The heading slide with the heading cloud
No.
regions / availability zones.
no.
Oh, okay. Now,
Yes, now,
Yes,
now,
yes, yes, yes.
yes, now.
my God. So maybe then I can go. So are you able to see now? Okay, now it is a okay. So this is the slide like cloud global infrastructure.
Yes,
Yes, yes.
Okay,
yes, sir.
all right. Okay. So maybe we have to survive with this. So as I mentioned, like probably like you might have missed, like and as I said that this is a pictorial format. So there are multiple regions, okay, and then within one region there are multiple availability zones. Okay, so region one example is the Mumbai is one region. That's the one key region for most of the cloud vendors. Okay, and within region there is availability zone one, another. There are three zones I'm showing over here. So those are three different physical locations. Maybe North Mumbai, South Mumbai, maybe the Pune, like that. So within within these physical locations zones, there are a lot of servers are there. And when I'm going to say that, I would like to procure 10 machines, okay, so you have to mention from which region and from which zones you want. Okay, so that's the way, like, you have to provision your infrastructure, basic infrastructures. Okay, my topic is the cloud native architecture. I'm not even started. This is a very fundamental level cloud computing environment. So my next slide is the cloud. Are you able to see this? Next slide is cloud regions and availability zones.
Yes,
Is
sir.
that visible?
We can see it. Yes.
We can see it. Okay. So look at this: the three popular, the cloud platforms like Amazon, Azure, and Google. So Amazon has 36 regions and 114 availability zones across the world. Okay, there are 36 regions, and within India, so they have provided the two regions. One is the Mumbai, and another is Hyderabad. So within Mumbai, there are three different regions. So this means three different, so they are physical data centers. So they have set up three different physical data centers. And Hyderabad also, there are three different physical data centers. So the whole India, so even from Kolkata, if I say that I would like to get some, 5 machines, so I have to either you have to choose Mumbai or I have to choose Hyderabad. Okay. So and this region and this this availability zones, so they are connected with the high-speed networking. Okay. If any data is created in one availability zones for a particular region, so immediately it will be replicated in another region. Okay, so this means there is a zero fault tolerance. So there will never be loss of the data. So cloud automatically, see, they are going to replicate your data within the availability zones. So similarly, Azure has got like 60 regions and 164 availability zones, and within India they have three regions: the Central India, Western India, and Southern India. And Google has 42 regions and 172 availability zones. Google has less, okay. And for India, they have set up two regions. One is the Mumbai, and they have set up 3 zones, and Delhi having 3 zones. So Indian users say, staying in Kolkata, I can select, I can create one machine which is residing in, say, North America. That is also possible. You can get a machine. You can say that give me a machine of having this much RAM, this is the storage, this is the network, blah blah blah, and which is there in Singapore. You can do it, but it will be advisable for faster or building modern applications. because you have to have the latency. So if you select a machine from say North America, so your latency will be high. If you select a machine which is there in Mumbai, your latency will be. But in cloud, there's the flexibility. And as I mentioned, that those multinational companies, that's why they pick and choose the relevant regions, because they have to run the business across the globe. So therefore, their virtual data centers, virtual machines will be spread across the globe, and the cloud is able to provide that backbone. So because of the cloud, it has been possible, and you can easily within one day you can set up the data center, okay, across your globe. So what are the next slide? It's the cloud compute engine. So if it is not visible, then only tell me, okay. Otherwise, let me continue. Suppose what are the basic compute engine? So basic compute engine is basically I want a few virtual machines, okay, and each machine you have to. If I say that I give me a machine, create one machine or compute engine, and which is residing in, you have to choose the region and zone. So I have to mention that Mumbai is the region, and you have to say that zone is say northern Mumbai. You have to mention all these things. You have to mention what is the number of vCPU, because the way you buy the laptop, buy the desktop, you mention basically what is the number of CPU. Here it's a virtual VC. Here everything is virtual. It's very same as physical. So you have to mention what is the number of vCPU. So its beauty is that you can create a small machine, maybe 0.5 vCPU. That is also possible, which is typically not possible when you are going to buy a laptop or desktop. You will buy maybe one, at least 4, minimum 4, 8, 16. Okay, but here you can start with a very small number of vCPU. You can start with even 0.5. You have a very small applications, very small. Maybe you will do the only Microsoft Office. You are working with that. You don't need a hi-fi machine. You want a very small one machine having maybe 0.5 vCPU. RAM, maybe you can say that 2 GB RAM. You don't need like 16 GB, okay, 48 GB or 8 GB or 4 GB. So that is so here you can go for pay per use. Okay, based on my need, I will start with the small and gradually I will increase it. So you start with creating a compute engine with minimal number of vCPU, RAM. You choose your operating system. Okay, you say I want Windows or Linux or Red Hat Linux, Ubuntu, whatever you like. There are plenty of operating systems that are available. It's just pick and choose. You have to have some kind of minimum, like general purpose SSD. Okay, then you have to mention basically like what sort of, whether you are a kind of nano type of engine or micro, small, medium, large. So you have to choose all this. It's basically very easy to select. You have to create a small network also, like the way you create a local area network. So you will create one virtual network. Okay, virtual private, where all your machines, if you say that for my institution, for my corporate, for my organizations, I need say 10 machines, few Windows machine, few Linux machine, few Ubuntu machines. Okay, some machines will be a kind of gigantic server, some will be very typical personal type of personal computer, desktop computers. So mix and match, you can easily create, and you create a network with them. It's very easy. Okay, so storage, obviously the storage is important. If you need to create a compute engine, is nothing but a virtual machine, so you need to provide a storage. So apart from a normal machine creation, you can have a share storage also. For you can create a like an object store. One of the example which is in is very little higher latency, where you can store, say for example, we are going to have a lot of documents, lot of say video images. Okay, so a lot of data that you infrequently access, not frequent access, not the transactional. So you can buy the storage, you can buy object store and store it over there, and those storage will be shareable over internet. So this means I can only buy one storage from cloud, and from my personal laptop, from here over the internet, I can store all these documents, all these video images, or maybe like any Word documents, PDF documents, Excel documents. Okay, even the data, archive data, You just keep it over there. It's very low cost. So those are the storage is also, so object storage is one of the key. Like data lake. If you are going to build a data lake, data warehouse, okay. So those data are not transactional. Those are typically used for modeling purpose, okay, for reporting purpose, okay, for learning purpose, machine learning. So you can keep the data into object storage. So that's why today's we don't really use the like big data. We use data lake, and data lake is basically internally they are using this kind of object storage for storing the informations. So these are the very basic building blocks for cloud compute. Network. So really, like when you are creating machines, how do you access it? You have to, and so you have to create the isolated virtual network so that it will be used only for your organizations. That is not going to be visible for other organizations. You have to have the subnet. You need to have the DNS. Then your machine should have a public IP so that you can access it from outside. Because when I'm going to create 10 different machines in cloud, so I have to access it. So there should be some public IP. So there are some networking setup, okay, which can be done very easily. So nowadays we don't need a kind of very very strong network engineer. So that we used to need like 10 years back, 5 years back. Here, a normal person who has a basic networking concept, he can easily configure the networking in cloud only. So everything is very smooth, okay, very agile. Okay, so then apart from that, you have to make a firewall, firewall rules. You have to set up the inbound, outbound rules. Okay, who can access, who cannot access. You can create several, kind of, connectivity, like whether you will go for the remote desktop. I have created 10 machines, 10 Windows machines. So obviously I'll build certain softwares in that machine. It's not my laptop. So from my laptop, okay, how to connect to that? So you have to create the secure cell, or you have to go by the remote desktop. Okay. So all this networking you have to set up, okay, by just a simple configurations. So these are very simple compute engines. It is nothing but you are going to set up the machines, set up the network, set up your storage, and then I'm gradually I'm going to focus on this basically like native computing, the auto scalability. That is a new feature only available in cloud, because as I mentioned that because of this cloud, the computing busting, okay, so you need to have your platform, have your compute engine, okay, you have to increase the compute engine, or you have to increase the capacity of the compute engines, okay, and that should happen automatically. So as I mentioned, during the festival time, okay, so in the e-commerce platform, the lot of orders are placed. So this means, like in other time, if there are say 1 million orders, so during festival time you will find 2 million orders per day. So you need to have your applications run on multiple machines, or so that is why the automatic auto scalability is important. So auto scalability, nothing but that is possible in cloud. You create a cluster of machines, say cluster of 10 machines. You mention the minimum and maximum count. You said that I will start with 2 machines and gradually increase up to 10 machines. Okay, so in cloud, okay, you log in over there and you mention that I would, within my data center, I would like to make a provision of maximum say 10 machines, but I will start with 2. So this means at the beginning you will see that 2 machines are running, and if there is a more workload, more number of users are coming, so it is going to increase automatically cloning another machine. So from machine 1 to machine 2, machine 2 to machine 3, it's automatic cloning. So when I say clone, so if I have a Java application running, or ERP application running, or any supply chain management application running on a particular server, so the whole server will be cloned into another server. It's automatic. Okay. In reality, if it is a physical data center, that is absolutely impossible, or it will take a lot of time. Here, within fraction of second, it will going to spawn create another server with the cloned application. This means whatever is running in application 1, running in machine 1, everything will cloned into machine 2 and is going to run. So auto scalability is required for building the modern applications. I'm going to move to the next slide. So this means instead of physical data center, now I'm moving to the virtual data center. So physical data center is not required. So we have to say, if today or tomorrow, goodbye to physical data center. Okay, everything will be the virtual. So this means within the virtual data center, so you will see, okay, like, there are, on the left hand side, are you able to see this? This is the cloud virtual data center architecture, realistic. So if you don't see, then raise your voice, otherwise continue. Okay, so you see the on the left hand side, the cloud. So how these data centers are created, you look at this cloud region 1 on left hand side, and right hand side you see there's a cloud region 2. I mentioned what are the regions. I say within India. So we have Mumbai is one region, Hyderabad is another region, Delhi is another region. Okay, so they are the examples of region. So this means for any, so if what will happen if the Mumbai is down with flood, because the frequent flood happens in Mumbai, so it gets disconnected. Okay, so therefore, like, you have to have your maybe region 1 in Mumbai and region 2 should be Hyderabad. It's a totally different data center. Okay, minimum 500 kilometer distance. Okay, there should be minimum distance 500 kilometer between two regions, and 100 and approximately 100 kilometers between two zones. Okay, so this means if there is a disaster in region 1, so the region 2, maybe Hyderabad, maybe Chennai, or like, Delhi, so they are going to take over of complete operations. It will be seamless. Okay, the users who are using the applications, they will never come to know. Okay, it is automatically switching. So that is a indicative, the realistic, data centers. Okay, like, region 1 we call it data center, and region 2 we call it DR, which is basically the disaster recovery center, and DC is the data center. That's the normal regular data center, day-to-day applications are running over there. But if anything goes wrong, if the whole region is down due to some catastrophe, so then the region 2 will be automatic. You can, in many cases, we select region 2 in European countries. Okay, if there is a whole India is in trouble, okay, then also there is no problem. You can have your setup in region 2 disaster recovery center in, say, Singapore, which is in Asia Pacific. So your application will run smoothly and there is zero impact on the users. So that is the beauty of this modern computing supported by the cloud. And this the basic, the cloud infrastructure related, the compute related services for these major cloud vendors. So I'm showing here like Amazon, Azure, and GCP, Google Cloud. Okay, so for setting up, like, what are the different terminology? Like in Amazon they said EC2, elastic compute 2, they call it. Okay, Azure they call it virtual machines. GCP, Google said the cloud, so compute engine. So these are different terminologies which are available. So we have to, of course, you have to select one particular, like, cloud, log in there, and select, like you say, mention that you like to create one compute, and you select that I want, like, 2 vCPU, maybe 4 GB RAM, maybe 30 GB in storage. You mention your local area network, and you create, like, how are you going to access it from outside, whether remote desktop, HTTP, etc. So you mention all this protocol over there. It is very easy. My next slide is, so what is there another, application architecture. What is the modern application? So everything modern. So we are discussing like this, the computing for the modern application. That is the heading. So what is the modern application architecture? Okay, so this is my traditional application architecture. This is a typical, like, 3-tier architecture. Like, you have we have some database. Okay, where we store the informations. Then we have a processing engine. Okay, like, Java based applications, or say Python based applications, C++, Node.js. Okay, where basically the collection of objects are there. Then you create a services layer. and those services are typically REST service, REST API. Okay, the APIs are very important today. Whenever you create application, we expose it through the REST API, because the REST API can be exposed over HTTP protocol. So over internet, if I'm in my machine, if I create one application and if I expose it over REST API, so from your machine you can easily call it. So you have to expose the REST API, so that it can run on HTTP protocol. Okay, so running, based on your Java applications, .NET applications, Python applications, whatever applications you create, you ensure that you are exposing the API. Okay, and those REST APIs, and then you invoke it from your applications, and from my mobile app, I can call it REST API. I can create on web applications, based on HTML, JavaScript, REST, React, or say, Angular, the lot. So from there, you have to call because suppose I'm running a mobile app, but your actual backend applications where the processings are happening, where this database and this objects, components, service are working. So those are residing into some remote machine, maybe in cloud, maybe in your local machine. But if it is in cloud, then it is very easy to expose over internet. If it is in a local machine or in data center, so you have to buy the domain name service. Okay, and then only it will be exposed from the internet. In cloud, it is very easy. You can do it in 10 minutes. You create one service and create the REST API and expose to the world. Okay. So these are traditionally this is the data layer, object layer, component layer, service layer, presentation layer. But the whole applications, if I'm going to create one, say for example, banking applications, and typically whole applications, say savings account, current account, or fixed deposit account. So typically those are built using one programming language, one kind of database. This is the traditional architecture. Other will go by like MySQL database with Java, and of course front end will be like HTML, or you say use the Oracle database, or say Postgre database. Nowadays you are using the NoSQL database, like MongoDB. And we are going to select the object-oriented architecture, component-oriented architecture, and we select the Java, .NET, or Node.js. But you use it is a monolithic, because the whole application is one programming language, one kind of database. But as I mentioned at the beginning, that today there is a flexibility. I can pick and choose my database, pick and choose my programming language, anything whatever I need to do that. Because I may have maybe a team of 20 people, so they may not be conversant with, all of them are not conversant with the Java. Maybe some of them they like Python, some of them they like .NET, some of them they like Java. So then how to build the application? So you want that flexibility. That is where the next slide is the modern application architecture is the microservice. So we started with long back, when even there was no C++, no Java, no Python. So it was a procedural language like C, COBOL, Pascal. At least in my time I've seen when I was doing the graduation. So then gradually we have seen this object-oriented programming comes. So this means you are creating a set of objects and the behaviors. Then 15 years back, we have seen the service-oriented architecture. So what is that? I want to mean that you create a service, as you mentioned, you expose the services. Based on your applications, you expose the services for any purpose. Maybe creating savings account. I would like to create savings account. So the savings account creation, maybe it is in Java program, you expose it to a REST API, and the REST API, whoever you want to call, your account will be created. So that is where the service-oriented architecture came 15 years back. And today there is a microservice-oriented architecture. That is the latest architecture in microservice. And one microservice is basically a very small functionality. It's not that that one microservice is whole complete banking system or complete e-commerce applications. One microservice is basically a small functionality. So you have to, next slide. You can think about here 5 different microservices. This is an example, like on insurance business. Okay, insurance business, there is a policy maker, then there is the policy renewing, then there is a claim settlement. Okay, that the payment is happening, risk modeling is happening. So one insurance business, so these are different kinds of business functionality. 15 years back, 10 years back, 20 years back, when we created the software for the insurance company, we built the complete software using one programming language, one database, and one front end. Today, we will follow the microservice oriented architecture, which are nothing but I'm going to decompose my functionality into small, independent, self-dependent functionality. Like policy making is one functionality that doesn't depend on claim settlement. So probably claim settlement is independent, which is independent from payment. Okay, so payment is independent from, say, risk modeling. So those who are the statisticians or actuaries who are doing the risk modeling, so they don't care about like whether policy is going to be sold out or policy has been lapsed. They don't care. Their objective is that. So you decompose the business functionality into small functional. Okay, a requirement, small independent functionality. Okay, and you call them microservice and let them run independently. Okay, maybe my policy microservice, which is a small functionality, let it run on one virtual machine. Maybe it's in a policy settlement, like claim settlement. Let the functionality run into maybe another virtual machine. Because you don't need to run all this business functionality 24 hours. As I mentioned, in the banking application, say in the banking application, when you are going to interest calculation, I think everybody will understand that. So interest calculation happens, it happens close to the end of the quarter. So probably the interest calculation is big module. Interest calculation that can be designed as a microservice, and that should run on a virtual machine, independent virtual machine. And that virtual machine, you don't need to run. You just run only at the end of the quarter. So you don't need to bear the cost for the virtual machine throughout your year. But in traditional architecture, we have everything running like 24/7. Okay, so it is better manageability, better resource management, better scalability. Because for certain microservices, which is nothing but a business functionality, okay, built in certain programming language. So certain business functionality which doesn't have too many users, which doesn't run 365 days. So every microservice will have its own nature. Number of users are it will vary. Some function like in e-commerce, in a retail e-commerce platform, like order placement. I think order placement, that microservice can be designed as a microservice because that is heavily utilized. Okay, whereas probably order fulfillment or maybe the payment or maybe the shipping, so there the usage is less. So you have to, based on the usage pattern, based on the independence of the business functionality, you design the microservices. Yeah, of course, and within microservice there will be object orientation. So but microservice is very, anybody who has the general sense about a business functionality or any functionality, they can decompose. So decomposition is important, and every microservice will run independently. One microservice does not depend. See, if suppose the policy microservice running on Unix machine, Linux machine, and claim settlement is running on a Windows machine, they are independent. If one machine is down, it doesn't matter, other machine is still running, still your claim settlement is happening. Okay, but in traditional architecture, everything running in one machine, and if something goes wrong, so all business functionalities are not available. Okay, so how this microservice will be implemented. So my next slide is the microservice decomposition. So you look at this is a airlines business. In airlines business, like these indicative microservices. Like in airline business, you think there are a lot of functions like there is a booking going on, there is a web check-in going on, the counter check-in going on, okay, boarding is going on, okay, billing, payment, the loyalty is going on, okay, the fare management pricing is a different key module that is also okay. So you can for an airlines application you can decompose into these microservices, and each microservice will run independently. Each microservice will consist of set of objects, okay, and they will run independently, so as if they are running into a different machine, okay. So that kind of flexibility is required. So it's a luxury, and that luxury has been okay possible because of the cloud computing. In my native in my local data centers, that is not possible. How many machines will buy? Can you buy machine 100 machines, 200 machines, 300 machines? No, it is not possible. In cloud is very easy. So from object oriented architecture to service oriented to microservice oriented architecture, so that is the modern computing, and the implementation will be possible because of cloud. Now moving to the cloud native computing services. So if you are not able to see, please let me know. Okay. So what is cloud native computing service? So cloud native computing is basically it is a ultra modern technology. Okay, we have never seen in lifetime. So we have seen. I'm giving an example. We have seen the virtual machines. So this means one physical machine, physical server, can be decomposed into n number of machines which call it virtual machine. Okay, so one big server I can decompose into maybe 10 different virtual machines. So if there are say 100 CPU machine and maybe 200 GB RAM and say maybe 1 petabyte of storage, so I can create like 100 machines from there. And each machine, I'll say for some machines I want 4 CPU, some machines I'll say 8 CPU, some machine maybe 16 CPU. Okay, so I can create n number of virtual servers. But can we think similar for an application? For an application means any application you create. Any application you create, like say order management applications, airlines applications, insurance applications, banking applications. Okay. So can we create the virtual applications? Answer is no. No means in today's data center, in today's topology, in the classical architecture, that is not possible, because you create your application using say C++ or Java or .NET or Python, you use a database and you deploy into a machine, maybe virtual machine. So using virtual machine, it's still one machine. Okay, and what your software is one binary and running one instance only. Okay, say for example, like say if I say that banking savings account applications. Okay, so that application is only one instance. So this means that is you are using your host machines or virtual machines memory. You are consuming the processing power. You are consuming the storage, and you are running only one application instance. Can we increase the elasticity? Can we create 100 instances of the same applications? Probably it is possible. I mean, then I have to provision for 100 different machines. Okay, because within one machine, like for this banking applications, I will have one instance. If I need to create the same application, if I need to run, probably I have to run into another machine. So how many machines I will buy? Okay, and how many times is it possible that then every time you are going to have a machine, then you like install your database? Okay. So do you like to make any comment, any question or? All right. So containerization is one key concept, that is the virtualization of the applications. So one applications which is running into your machines, within few seconds, you can create 100 different instances. And each instance will have its own operating system, own memory, own installation, binary, its environment variable, everything. Okay, it will have own version. So the way we can create a virtual machine, we can create a virtual applications, which is nothing but container. Okay, so because of this container, okay, it has been possible to achieve the infinite scalability of an applications. So doesn't matter, like today for e-commerce applications, Amazon, for example, e-commerce, today it is whether 1 million users or 10 million users, doesn't matter. So today it is possible to achieve the infinite scalability because the cloud vendor have their necessary hardware in the backend, and because of this containerization techniques, containerization architecture, you can virtually create within few seconds a number of these. So the containerization, will talk on this. It goes to certain the image creation of the applications. Then there is a image, Docker image, Docker registry. Then you have to create the containerization, then create container orchestration. Okay, I'll talk on this. Okay, those are the basic, building blocks of containerization. Another interesting, cloud native computing, the serverless computing. Okay, see, even if you go for containerization, but still for one machine you have to set up it, like, you have to set up your, binaries, like if it is Java, then you install the, maybe Tomcat or Apache Tomcat. Maybe you have to, like, Java Spring Boot library, you have to Maven library, then Hibernate library, JDBC library. So many things you have set up the environment. All these things you have to do at least once. Okay, and then after that, through containerization technique, you replicate across. Okay, in serverless compute, it's interesting that you don't need to do anything. Okay, you just write a program. Okay, and you say that I would like to run this program using Java. You write the program in Python. You just mention that I would like to run the Python using the Python environment. So you just select one environment. You don't need to install. You don't need to think anything. Okay, no config, nothing. You just write the program and run. Okay, so have your binary ready. So if it is a, like, Python program, ensure that you are going to have .pyc file. If it is a Java program, you ensure that you have the .jar file. Okay, if it is a Node.js, you ensure that your .js file is ready. So you have your binary ready, and just, in cloud, and go and run. It's a nanosecond billing. It's very small, amount of money, very, very less, and you can run it very easily. Okay, so I'll talk on that. And the monitoring, obviously, like, you have to monitor, like, in the whole cloud native environment, which in turn is going to use the cloud computing, the computing, storage, network. They're going to utilize it. So, like, what is cloud native service and how it can be implemented? Let's see in the details. So as I mentioned, that next slide is container. So what is container? Okay, so container is nothing but, look at this dotted lines box. A container is nothing but one applications running on operating system and running on a runtime environment. And if it's Java based applications, so to run an application, you need the operating system like Linux, Windows, Ubuntu. So select that runtime environment. If it is Java, then you need ability, like JDK, Java runtime environment. Lot of Java files are required. Tomcat, for example. Okay, then you need to have this. Then you need to have, like, Maven. Okay, to build it. You need JDBC. You need to connect to the database. You need Hibernate. So a lot of jar files are required. So all these things will be embedded within the container. Then your applications, like, if you are writing the Java program for say interest rate calculation, you will write probably 100 lines of program. So on Java or .NET or Python, so that is the application. The whole thing will be bundled into a container. Okay. So this means when I'm creating a container somewhere, so that container will have its own operating system as if it's a different machine. When you run a container for say interest calculation, so it is going to have its own operating system, runtime, and its runtime binary and application binary. So container has the minimum set of operating system features needed for the application to run. And a container is nothing but a Linux process. Basically, it's a Linux process, okay, running on any host machine. Your host machine may be Windows, that's the beauty. But when you create a container for say banking interest rate calculation, it will be a application, maybe Java based, maybe .NET based, Python based, running on a Windows. So it is going to using the containerization technology, you will be able to create a number of, okay, as I said, the container is nothing but a virtual instance of the application. You can create 100 different instances for same application, like interest calculation for bank, or same applications for order placement for, like, Amazon e-commerce or Flipkart, for example. Okay, so same application you can create 100 instances. Okay, and each instance will have its own operating system. But you are not going to buy so many machines. When you think about operating system, usually we buy one machine which will have operating systems. But here I'm talking about one particular functionality, which is nothing but microservice. Okay, not the whole applications. So for one particular business functionality, okay, like say banking interest calculation for fixed deposit. For that, I can create 100 different containers, okay, and each of have its own operating system. So that kind of virtualization is possible. And not only that, the container will have its own IP address. You can monitor it, independently. So you will feel that those are different, as if they are running on different machines. My next slide is, so what is container? So I just said that VM, virtual machines, are abstraction of physical hardware, and containers are the abstraction of the application layer. Okay, a container runs as a separate independent process. One container is totally independent. Maybe the same application, maybe the interest calculation, okay, banking interest calculation, that is the business functionality. Same code, same code, everything same, but it is going to create a number of independent processes. So one container down doesn't mean the other container still up. And it has been possible because of Docker, which is the leading software container platform. Okay, so this means that using the Docker, so this means you have to have Docker to be installed on each machine. So if I create one virtual machine, VM, okay, from cloud, and if I install Docker on the top of that, it's a one machine, virtual machine. You can create n number of containers on the same machines, and each container will have its own operating system. So more details. So how it runs? This is my Docker container platform. So look at this. There is on the left hand side, the Docker container on physical machines, and right hand side Docker container on virtual machine. Okay, so I can have a physical machine, or I can in cloud. It is only virtual machine. So I will have my host operating system. Okay, if I on the left hand side, if it is a host machine, then I will have a host operating system like Unix or Linux or Windows. Then install the Docker, and on the top of that you put application A, application B, application C. Okay, each of them will have the container. Rather, they are the different application. Maybe application A is interest calculation, application B is maybe savings account creation, application C, okay, might be loan applications. There are variety of applications run in a banking business. Okay, so those are, you just create like A, B, C, those are all microservices. So you have to split, like, the business functionality, small functionalities, and they will run independently. For application A, okay, it is going to create n number of containers. Application B is going to create n number of containers, okay, which will be possible if you have the Docker to be installed. So you have to run. So Docker is going to decouple from the physical machines or maybe the physical operating system. So it is going to isolate you. So you have to do everything on the top of the Docker. All right. So if it is a virtual machines, so on the virtual machine you will have a on guest operating system right hand side, like some virtual machine maybe Windows, some virtual machine I can have Linux, some virtual machines I can have Ubuntu. Okay, and you ensure that on the top of that the Docker is there. Okay, and then once the Docker is there, and then you can create your application ABC. In this case, those are all microservices. So they are all small, the functionalities which will have the independence. Okay, so when I say again, I'm saying these microservices, like in airlines business, I mentioned that booking is one microservice. You have to develop booking, okay, independently. You can, that billing is another microservice, boarding another microservice, web checking another microservice. Okay, and you can develop them independent language also, no problem, because they will run independently. So I'm moving to next slide. In the cloud native, like, what is this container registry? So there is a look at this. One is that image creation. So for any containerization applications, so once your applications programming, okay, all these things are ready, so then you have to package it in an image. So typically, if it's a Java application, we create a jar file. Okay, if it's Python, it's a .py. So, but that jar file, you have to bundle it with a lot of things, whatever is required because jar file cannot run on its own. So jar file needs the Java runtime environment, okay, the application server runtime environment. So whatever runtime environments are required, so everything will be bundled together. Not only that, operating system, and not only that, it is going, you have to provide that how much memory, how much processing power is required. You have to add all these things to the, okay, so that it can run independent, as if it is running independent machine. So creating Docker image on fundamental activity for native computing, cloud native computing. First, once the application programs are ready, okay, then after that, next step is basically you have to create an image, and in the image you supply everything, whatever is required. You mention starting from operating system, what kind of jar file required, and how to run the, suppose it is a Java applications, so typically you say Java minus jar, then abc.jar. You mentioned that. So you have to mention, and what are the different environment, maybe suppose typically in Windows, Linux machine, or so you set up a lot of environment variables. You have to mention those environment variables also, so that it can create a whole bundle, and that bundle will be supplied to different machine. From the image, you create the instance. If I create one image for, say, savings account creation in banking, then I can create, say, 5 instances, 10 instances of the same. So as if the 10 instances are running, okay, at different places, and say today I have one instance, maybe like 100 users are trying to open the account. Now, next time, like tomorrow, the 200 users are trying to open the account from over the web. So in the backend, they create easily another instance. Then third day, they can create another instance. So that instance creation, which is nothing but all the binary, all these operating system, resource, okay, environment variables, everything are together bundle. Okay, within 1 second, it is going to create the instance. Okay. So that is absolutely impossible in the traditional, application architecture. So in Docker, that you create the image and you register it. Okay, so you create one image for maybe airlines booking applications. You create image for like airlines billing application. You create another an image for maybe web check-in applications. You create another image for maybe like boarding application, because everything is application. As I mentioned that the microservice architecture. So this means you think about the 10 microservices are there. So you build them using your own programming language. Okay. And then, so those are all independent. It's not that you have to develop all of them in same programming language. You develop independently, develop them, then you create the image and you register the image on right hand side. I'm saying this Docker registry. Okay. And from the Docker registry, there are a lot of Docker commands like Docker build, Docker push, Docker run. So Docker build is nothing but Docker, it is going to build the image. And Docker push is going to push the image in the registry. Okay. And then Docker pull means it's going to, from registry, it's going to pull the image. And when you say Docker run, it's going to create the instance of the application. The moment you run the Docker run, followed by the image, say, for example, like, airlines booking.jar, just for example, the moment you will say Docker run, so immediately, like the booking application is up. Now the users can start to go for it. They can utilize the application. The moment you say that Docker run, say billing, so the billing can be run. Docker run, say pricing, so your pricing application will be starting. And so if you say that Docker run 10 times, it is going to create 10 different instances. So it's a kind of near impossible things which has been possible today, very, very easily. Okay, in traditional architecture, you have to buy machine, you have to set up environments, set up runtime, lot of setup. Okay, here you are creating, if you can intelligently create the image, so that from the image within fraction of second you can create the instances, and that instance will be created in different machines also. It's not only one machine. You can have say 5 machines and and you can create 1000 instances. I'm coming to the next topic, is what is the containerization process. So this is the containerization process, the create application binary first. So you create jar file, war file, .exe file, .dll file, depending on the technology, .pyc file, .js file. So those are the typical application. Once you create application binary, means write the program, compile, and it is going to compile and create the packaging. So we'll create this kind of things. Then you build the image. So look at this. So Docker image is nothing but application binary, runtime library, environment variable, runtime commands. Okay, runtime command means to kick off, like Python. To run something, you give a command. To Java, you give a command from the C. So how to run? So everything is bundled into the Docker image. Then you register the Docker image. You have to go for the registry. So it is going to register in all the images will be stored into a central location, which is called the Docker registry. From Docker registry, you pull and run. Now it is going to create container. You see, look at this. So many containers from the same image. Same image, maybe I have 10 images and one image is, say, airlines booking. So for the airlines bookings from the same image, I can create, in this case, I have shown 3 different containers. So 3 different instances, 3 different instances of the airlines booking. So and look at this, on left hand side, I have shown a virtual machine, or right hand side, I have shown a physical machine. So this container will be created. Infinite number of containers can be created and into different machines. So within one machine, you can have n number of containers. And as I mentioned, one container means it is having its own operating system, own processing, own binary, own set, everything set up over there independently. Okay, but actually it's one virtual machine. Okay, and the moment you run the container, now your application is up. So now if it is web-based application, you just go and make a booking. You can make a booking, I can make a booking, he can make it, she can make the booking. Okay, so if the number of users is growing high, you have to create container, because by present, suppose I started with 2 containers, But now the two containers are not able to take the load because today's number of booking is less. Think about say airlines, because of airlines disaster. Okay, Air India disasters. So maybe today the less bookings are happening, but tomorrow, but one fine morning you will see the number of bookings is very high. So in that case, you have to set up the environments. You have to set up the cloud native computing in such a way that it can create container dynamically. When the more and more users are joining, trying to create the application. So that is impossible because of the cloud native computing, and especially it's because of the containerization technique. But then who is going to create the container? But Docker doesn't have this kind of dynamic, So using Docker, if you say if you say that Docker run, it will create one instance. Say Docker run, say booking.jar, booking.image. If you say that Docker run, say billing.image, so then it is going to create one container. But you need to dynamically, you have to orchestrate it. You have to dynamically create the containers. So who will do that? So that is what the technology that requires the container orchestration technology. So this is a slide for container orchestration. So what is container? That is very interesting technology. So there is a difference between container and container orchestration. So container means container means you create image for a particular microservice, then you register it, and then you run it. So typically Docker build for creating image. Then you say Docker push. It is going to push the image to registry. Then Docker pull. You pull it from registry, and then you say the Docker run. The moment you say Docker run, it is going to create one instance. But I said that in cloud, I need this infinite scalability. So it should automatically, depending on the load, depending on the demand on the application, it has to create dynamically new containers. Okay, so who will do that? So that is what the container orchestration require, who can create based on the need, who can create the containers into various machines, because your machines are limited. You are going to buy maybe, you're not going to buy 1,000 machines. You're going to buy 10 machines. Okay, so within 10 machines, and you have say maybe 100 or 500 microservices. Okay, so those 500 microservices, each of them is basically different functionality. So for each of the microservices will run n number of times. So maybe first microservice, say booking, which will run maybe say, for example, 10 times. You need to have the 10 different instances, 10 different containers. Maybe the airlines booking billing, I need 15 instances. Maybe web check-in, that is another microservice. I need maybe 20 instances. So this means 10 plus 15 plus 20. If you add up, you will get say maybe 400 instances. You need to start 400 containers. But who is going to do that? So container orchestration technology is going to dynamically create that new containers. Okay, so it's a infinite scalability. Not only that, it can add a new machines also, because after some time, like your one, because you might have started with say 5 virtual machines, and each virtual machine is having their fixed number of vCPU and RAM, virtual vCPU, and storage, but it doesn't have the capacity to run anything and everything. So dynamically you have to run the new machines also. So adding up the new machines and adding up the new containers. Go to the previous slide. So I have shown one virtual machine here. Okay, so you might have to add more and more virtual machines, and within those virtual machines, so this means if I right now have 5 virtual machines, I might have to create another 5 after that, because my number of containers demand is more, because I have to create more containers. So therefore I need more resources, and who is going to give the resource? Your virtual machine. So therefore, dynamically create the virtual machines, dynamically create the container services. Okay, that is one of the key requirement for infinite scalability. So container orchestration is the technology. It's a different technology. So it does that. So what are the building blocks? So it said it's a does orchestration of containerized application and scale the capacity. We create more and more containers. Then create a cluster of nodes. Each node are nothing but a virtual machine. So you have to create a cluster of 10 nodes, nothing but cluster of 10 virtual. You have to start with that. Then you have to launch the node dynamically with the Docker and orchestra. As I said, to run a container, because the application will be started when you say the Docker run command. So that if you need to run a Docker run, so you have to ensure that your Docker software is installed. So who is going to do all these things? So orchestration will automatically do that. It is going to not only that it is going to pick up a new virtual machine, but it's going to set up this Docker environment readily available to you. Okay, and not only that, it is going to create a container of that particular image. Say particular image, for example, say booking, airlines booking. I have created one image. So for that image, it can create instance 1, instance 2, instance which are nothing but container. So you need a orchestration technology which is going to create more and more containers, which going to, and to create more and more containers. So you at certain point of time you might have to increase the number of nodes. So then the managing the containers. Suppose the load is less. Suppose today, 2,000 users are trying to create the. Suppose the Air India now the number of users is less. Okay, because of certain disaster. So now the orchestration technology that has to reduce the number of containers, it will automatically done. In physical data center, it is absolutely impossible. So the management is important. Create, update, delete the containers across the cluster of nodes is important. Then allocate the container level CPU. So you have to supply the resource to run the container. As I said that you need operating system, you need CPU, you need memory. You have to assign the port, because every container has its own port. You will find a public port which is you can over the internet. You can over the internet you can monitor the that container. So you have to allocate that. Who's going to do that? The container, the Docker itself cannot do that. Okay, so allocating the resources to the container is a responsibility of this container orchestration technology. Okay, and as I said, the scale up and scale down containers. And what is the technology? The Kubernetes is the world's leading container. This is the leading container orchestration technology. Okay, for any application that we're thinking today, behind the application, you need to have this cloud native computing, which is nothing but you need to have the Docker, you need to have this Kubernetes, you need to have the serverless computing. So this is the pictorial format of this Kubernetes. So Kubernetes, they use it, there is if you look at this node, so each and every node is nothing but a virtual machine. And within node, you see the pod. So pod is the terminology provided by Kubernetes. Okay, so pod is nothing but the container. Okay, it is the one pod 1, pod 2, pod 3. See, lot of pods are distributed across. There are in this diagram there are 6 nodes. This means 6 virtual machines are there. But within 6 virtual machines, there are 24 containers are running. Nothing but 24 pods are running. Okay, so today there are say 24 containers. If I need maybe another 20 containers, if I need to add, so you might have to add one virtual machine. So it's not that 1:1. So within one virtual machine, you can run maybe 100 different pods. Okay, so one pod for each and every pod, as I mentioned, for each and every pod having its own public IP address. You can monitor it over internet. So as if you will feel that one pod is one machine, because it's going to give you the IP address and port number. Okay, but behind the scene there is maybe only 6 machines I'm talking about. So that should be some 6 different IPs. But actually, once you create the pod using the container Kubernetes, so Kubernetes is going to do all these things. It is going to provide the resource. It is going to run the container. Yeah, provided you have your image ready in the registry. So Kubernetes is going to pull the image from this container registry, and it is going to make a run command, it is going to run it, okay, in one of the, so in which virtual machine it is going, its container is going to manage that. So container orchestration Kubernetes is going to decide like in which virtual machine or in which node, what kind of like, pod will be created. So all this balancing will be done by the Kubernetes. Okay, we don't need to bother. We have to, no, we have to just configure, we have to mention, we have to ensure that my application code is ready, my binary is ready, that my image is ready. Okay, you just register and you configure the Kubernetes. You say that I will start with a cluster of 6 nodes. You mention that, and you mention that I will start with maybe 24 pods for say my booking, airlines booking. Maybe you say that 15 different pods for say airlines billing. Maybe 25 pods for say airlines web checking. You just mention all these things, okay? And you have to start with this, and then when the more load is going to come, it is going to create dynamically the more and more pods. And when there is a reduced load, it is going to reduce it is going to kill the pods also. If it is some of the pods are not utilized, because using one pod, as I said, that is one application, like in maybe 100 users, 100 users can peacefully use the one pod. So one pod is nothing but one applications. And one application running means what? The set of users they can use that software, that they can create the booking. It's not that for every user, there will be one pod. No. So one pod means one application running, and then a sort of users can go for the booking. Okay. So in Amazon e-commerce, when Amazon income millions and millions, they are going to use the application. Maybe in the behind the scene, they are having like maybe 50 pods or 100 pods. It's not the like 1 million pods are running. See, this is the container, the orchestration concept. So the container orchestration, that auto scaling, how it happens, the pod you see, look at this, number 1, the pod in pending state due to insufficient resources. Okay, the pod is, you have your number of users are too high, but your resource, for example, you mentioned the number of virtual machines is 10, and it is not able to manage it. So it will be waiting. The moment you will say that from 10 to 20 through the auto scaling, okay, so then automatically it is going to get the new machines, and it is going to create the machine. Number 2, the increase the desired number of instances. Okay, so to increase the instances, or increase the number of pods, or increase the number of containers, okay, so you need to have these virtual machines. So the moment it is going to get the virtual machines, so it is going to automatically create a new pod. So 2 factors. One is that adding a new node or virtual machine, and then another is the adding new pod. So these 2 things happens parallelly and managed by the auto scaling capability of cloud orchestration technology, or nothing but the EKS, nothing but the Kubernetes services. So I've talked on this Docker, that is fundamentally is required for creating the image. So this is the new concept, okay, image creation, which are not there. So you create image, okay, and from the image you create instances, or create the pod. The pod is the terminology given by this Kubernetes. Okay, so that way you can create more and more applications, in your environment. Serverless computing is, as I mentioned, that you can just run code without thinking about the servers. So at least in Kubernetes environment, in container environment, at least we have to choose the number of, somewhere you have to say that my minimum number of virtual machines is 2 or say 5, and maximum number of virtual machines you have to mention 10 or 20. You have to mention that. Okay, and you create the image. But here in serverless technology, you don't need to create any. You just write the program. You just write the program and just create the binary. Okay, and choose your own technology. So as if you are running without any server, you will feel that. So I do not need to bother about, like, whether my Java environment is there or not. I don't need to bother about whether my Python environment is there or not. Okay, you just choose that I would like to write the program. There will be some drop down. You say that Java, or you choose the Python. Yes, you have to select the version, of course. Or you say that certain .js, like some JavaScript, like React or Node.js, you mention that. And the code will run automatically. But this is used for typically a stateless and event-driven architectures. So far we have seen in industry not a very kind of very gigantic heavyweight application. It's a very small stateless function which doesn't depend on the state of others. Suppose if your some process is running a long running process, probably that is not suitable for serverless, because in serverless, it is going to run and stop. So, for example, you are going to certain sorting or searching algorithms. You like to run the program. Okay, you like to go for executing a Python program, which will that maybe it is going to sort one file and find certain ORs, for example. So that kind of function which doesn't take longer time. Okay, because you can think about one application where there is some kind of infinite for loop or while loop. So this means it's a long running program. Okay, so that is not a good candidate for serverless. It has to be stateless function. Like you say that calculate interest for a fixed deposit. So it doesn't matter. It's going to pick up, like, what is the principal amount, what is the interest rate, what is the duration, and it's calculate and stop. Okay, so that way, like, serverless computing is suitable for a stateless function, and it is more suitable for event-driven architectures. So event-driven architecture means when certain event happens, okay, then take the action. Some credit card fraud happens, you handle it. This is a classic example. Suppose some fraud has been detected, because the fraud detection algorithm or fraud detection logic is in machine learning, or some complex event processing is running, and it has detected there is a fraud. So the moment it will happen, so you have to maybe stop the credit card. So this means stopping the credit card. That should be can you please mute, please? So the serverless computing is one of the excellent features of cloud, where I don't need to run your code without thinking about server. Okay, and I just said that it is used for a typical event-driven architecture. Okay, and the action part, once the event happens, then you take action. So that action part, that logic can be implemented in serverless computing. Okay, so platform to deploy, run, manage applications without complexity of building and maintaining. So without thinking about, like, buying virtual machine, setting RAM, set up this, set up that. So this means, depending on the nature of the application, for certain functionalities, I can design using serverless computing. For certain features, I can think about containerized part, and certain features I may use even, like, in the classical part without any containerization. Okay, so whenever there is a more agility, more scalability is required, so where does containerization require? More scalability is required for a serverless functions. For the stateless functions, you need to use the serverless computing. So in serverless computing, it just it's a sub-second billing. It's only suppose write a Java program, say for example on search, on binary search, for example. You run a program and run it for binary search, and it will require maybe few seconds. So only the few seconds billing will be required. It's very small amount. Okay, as I said, the event-driven architecture, okay, very important. And as I said, there's abstraction of server. Basically, there is abstraction. You don't need to care about servers. Okay, whether you have a Unix machine, Linux machine, or whether you have a like what kind of big machine, small machine, and what kind of operating system. So all these things, nothing is required. So in the cloud native, the computing, the primary technologies, for cloud vendors, like if it is Amazon, if it is Amazon, so they provide. So Amazon has got its own elastic container service, and also they have there are two types of service. One is that ECS, elastic container service, another the EKS, elastic Kubernetes service. So Kubernetes is the most popular one, but Amazon has provided that is own orchestration. As I said, that orchestration of containers is required. So it has got its own orchestration. They have used the Docker as the open source, but they have built their own orchestration logic, and given the product name is ECS, Elastic Container Service. And along with that, they have a Elastic Kubernetes service also. Okay, so and they said the Kubernetes based products are important, because as you look at the Azure and Google, so Azure has given the Azure Kubernetes service, Google has given the Google Kubernetes service. So if you know how to configure in one cloud, another cloud is very easy. It's very, very similar. And the same open source have been utilized by all cloud vendors. They've created more and more lapas, more automation logic they have added over there. The container registry that Amazon has given the ECR, Elastic Container Registry. Azure has given the Azure Container Registry, and Google has given the Google Container Registry. So as I said that, so registry is nothing but the place where all the images will be stored. Okay, you need to you have to enlist all the images, okay, which have been built on the top of your application jar files, application jar file, wall file, or DLL file, .exe files on the top of them. And the serverless technology, the Amazon has given the name Lambda, Azure has given the Azure Functions, and Google has named Google Cloud Functions. So these three technologies are the founding technology for building any type of modern applications. Whether you are running Java applications, whether you are running a Python applications, whether you are running Node.js, whether running a database, whether you are running a NoSQL database, okay, so whether running a Spark program, so anything and everything, it should run on containerized or the cloud native platform to achieve the infinite scalability. I want to talk on this API gateway, and this is one applications which is for supply chain. I had worked, while I was in TCS, implemented on supply chain logistics applications. So look at this, the Kubernetes, okay, and so that is the heart of the engine, okay. So for running all these applications, I won't get into the details, okay. So lot of applications, lot of business functions, a lot of technologies are mentioned over there, but today's topic was the cloud native architecture, cloud native computing, and whatever you are running, okay, like here it is showing this Java Spring Boot, okay, Java based applications, and that will run on Docker and Kubernetes. You look at this cloud managed Kubernetes engine, okay. So I would like to end with the key technology names: the cloud basic computes, the compute network storage, those are the basic computes, and then followed by there is a containerization, which is registry, and then container orchestration, then the serverless technology, and then finally like the microservices, which are the building blocks of the application architectures. So all of you have worked with the object-oriented programming, object-oriented. I think everywhere this that, but today's architecture is not object-oriented. It is required, but you have to go one step above. You have to design the microservices, which is nothing but the decomposition of your whole business domain into small independent business functionality, and you build them independently, run them independently, scale them independently. That is the philosophy of cloud native architecture. So with this, I would like to end the session. So if you have any question, I can take it up. Any question? If you have any question, I can still, there are 4 minutes time. It is 1 p.m. is the closing time. You can write in chat window. Okay. So thank you very much. So is there anyone from organizing team? Sudeep?
Thank you, sir, for your session. Right now, I have a small memento to show you, sir. Sir, this is a small memento for your fabulous speech. On behalf of Greater Kolkata College of Engineering and Management, this is presenting. Sir, can you see it?
Yes, yes. Yeah, thank you very much.
Okay, sir, you're welcome. For the last session, you may join at 2 o'clock. Now the session ends. Okay.
Thank you.